I'm Ian Hoffman from the PTS.
And we are pleased to welcome you to session 3.6, analysis of radionuclide monitoring data. We have 3 exciting talks this afternoon. Before starting, I will just remind that the lightning session associated is tomorrow morning at 10, followed by the e-poster session at 11.
And with that reminder, we'd like to get started with our first speaker, Brian Milbrath from Pacific Northwest National Labs. And Brian, your talk should be queued up here for you momentarily.
It's good to be here in Vienna. Good to see you. It was interesting this morning, one of the keynote speakers mentioned machine learning for radionuclide analysis, and I get to talk about my first foray into trying to do that. Along with my 2 data science colleagues at PNL, Alex Hagen and Christian Svinth. I have a clicker. So the IMS produces a lot of interesting data, and the quality of that data is very important. It can be corrupted or have just noise issues, detectors degrade and so forth. And so some way to automatically monitor the quality of that data is needed. And this was kind of a case study of ours based on particulate spectra data from IMS to see what machine learning could do in that regards. And shown in the slides are several spectra there. The gray one is kind of the average spectrum for this Canadian station, and then the orange ones are various very different spectra from the average from that station, many due to electronic noise or something. So for our study, we use supervised learning. That's where the machine learning, the network is trained on labeled data. We used 5 years of data from 29 stations at over 200,000 spectra, 80% for the training and 20% then for the testing. One of the very first things we had to do was get all the spectra to have the same number of channels. And of course, the goal in your training is to minimize the difference between actual and predicted values of what your resulting network. It's interesting, the data scientists, the first thing they did was they trained their network to predict the location on the globe given a spectrum. And so the network produced a location on the globe that minimized the Haversine or Earth surface distance from prediction to real location. And then I said, well, of course, all we really need to do is pick the right station. We don't have to pick the exact location on Earth. And they did a second pass where they came up with a classification system done with cross entropy, which is measuring the distances between 2 probability distributions. We used 3 types of neural networks. Multi-layer perceptrons are ones where your neurons are fully connected. In other words, you have information immediately connected from one channel to every other channel. Much less computational is the convolutional neural network, which is good at learning features. You could view it as kind of filter optimization is how it operates. And the third type is a newer machine learning approach called transformer, which is useful in that you can have different numbers of channels, because what the transformer does is it groups data and moves on from every single channel. But in truth, the results, because the truth is IMS spectra are very rich data set with a lot of easy ways to come up with what statisticians call distances, that we got good results no matter what neural network we used. Greater than 95% of these location predictions were within 150 kilometers of the true location, which of course was a station, and greater than 97% of our station classifications worked with this supervised training. This matrix may be a little too small to see on the screen, but the x-axis are the predicted stations and the y-axis are the true stations, so everything on the diagonal is correct. Everything off diagonal is miscorrect. What's interesting in this picture, and the scale on the off diagonals goes from 0 to red or purple. The largest misclassifications are in the order of 5-6%. But what's interesting is, and it's probably too hard to see, a lot of the misidentifications are, I don't suppose I have a laser, no. A lot of the misidentifications are like one Canada station for another Canada station, or one Russian station for another Russian station, or one Canada station for a US station. So, and it's a little harder to see, but polar on the two ends of the Earth. So there's clearly some local climate factors that come into play. Every spectrum on this slide is a misidentification. In terms of entropy, the ones in the top rows, the lighter ones, those are higher entropy, Shannon entropy predictions, which means a lower confidence prediction. And so what you see there, when the network had low confidence, were things like electronic noise and so forth. It had low confidence in prediction because lots of stations have electronic noise. Your ones at the lower extremes where you had low entropy predictions, which means more confident predictions, tended to be things like a new nuclide showing up in a spectrum or so forth. It would be confident about its identification, but wrong because these were things it was seeing less often. Just to take a closer look at the mispredictions. So, for example, Canada 15 there, CAP 15. The orange represents its average spectrum. And the gray is the average misprediction when it's confused with Canada 16. And all of these represent ones where you had at least 10 mispredictions of one station to another. And so what you're seeing is when Canada 15 gets more active, it starts to look like Canada 16. Or when US 76 starts to get a little less active, it starts looking like Canada 17. Again, your neighboring stations seem to be somewhat related, and that's when they start getting confused, is when something changes that makes them look more like another station. So given that initial study, you could start to maybe think about how you could operationally do some anomaly detection with machine learning. You could use machine learning to automatically detect things like data quality issues, detector issues like the gain is shifting, or interesting things where the station activity is changing. It's seeing nuclides that it doesn't normally nuclide. I think with a little more work, there's some interesting thing there in regards to, because of this seeing that neighboring stations were often confused with one another. I think with some study of connecting to ATM and climactic regions and so forth, there will be some further interesting things. For example, when these two stations, the Japanese station and the Russian station, look alike or confused, maybe that represents periods when strong fronts, we didn't look into this, but I think it's an area of study, when large fronts go across Asia, or perhaps when the particulate load in the atmosphere due to things like Siberian fires is generating a lot of similar activity. Things like that, I think, would be interesting for further study. So supervised learning is ideal for easy tasks, and to operationalize it, you would need to come up with some metrics. So, you would want to pick your false alarm rate you're willing to live with. that you're going to investigate things. Dimension reduction would help because of this issue with different channels for different detector types. And an important thing is you have to, figure out how you're going to retrain if you use supervised learning. Because if something substantial changes, like a new detector or something, you basically have to start over with supervised learning. And that's why when you put machine learning into operations, in most cases you wind up using what's called unsupervised learning. In unsupervised learning, you do the appropriate dimension reduction to handle those things that regularly change in your system. And then you can do things like two-sample tests or other statistical techniques on your reduced dimension space to better operationalize your automatic analysis. And of course, in truth, you can also use machine learning can guide signature discovery. We saw some interesting things just in this little study of ours. But truthfully, some of the things we saw as anomalies, you don't need machine learning to figure out, right? You know what a noisy electronic noise spectrum looks like, but machine learning can help you identify issues that you have, and then you could go to non-machine learning techniques easy enough to automatically detect things like electronic noise and so forth. So in conclusion, particulate spectra in the IDC sometimes have anomalies. Those can be electronic noise, reporting issues, or some other mistake. Assuring the authenticity and quality of data is critical to the IMS's performance. There's a lot of information in there. We found it relatively easy to apply machine learning to it. Supervised neural networks can predict the I expected to be able to find anomalies. I did not appreciate how good we could do at picking the correct station of an IMS spectra. We got greater than 97% of being able to classify the station that an IMS spectra originated from. And those mispredictions were often indicative of some interesting anomalies. So I think the spectra are ripe for further work in machine learning and ultimately operationalizing the technique to help in automatic analysis. Thank you.
All right, thank you very much, Brian. Does anyone in the audience have any questions for our speaker? Please.
There was.
It's coming. Matthew.
Thanks, Brian. Nice talk. For classifying the station location, was it all done kind of independently, or did it go in a batch mode of saying, okay, let me bin these stations with the right spectra, or was it all? Well, they could be anywhere, I guess. How did they do it?
So, the data was all labeled, but then it came up with, in the case of the classifier, it came up with, the network would come up with 29 values for the 29 stations, and that the one with the lowest entropy value, which kind of represents, you could think of that as comparing two probability distributions. It would pick that particular station for the classifier. If that answers your question, okay.
Okay, thank you. Any other quick questions for our speaker?
Thank you, Brian. Our next speaker is Sophie Liljegren from FY.
everybody. Today I will be presenting some work I've been doing with some colleagues, Sofia Brander from BFS and Ule Ross from BGR. And I'm gonna, explain, this is the clicker, yes, thank you. I'm gonna talk about a radio xenon event that we saw over Sweden in the Swedish cube array, but also in several IMS stations in November and December 2022. And this was a fairly anomalous event. It was a sum of the highest radio xenon levels ever measured in the cube array, in the Swedish array. And the aim of this work was to firstly identify the source and understand the source term for understanding the radio xenon background in Europe, which is very important for CTBT purposes. But this was also an excellent opportunity for us to compare what a cube array, so array of SANA cubes, could accomplish when compared to the IMS system. Just to start introducing the data, this is what the situation looked like at the time in Sweden. So what you see on the map to your left is kind of the setup of the radio xenon systems in Sweden in November and December 2022. So the green scatter points are the cubes, so which were a part of this, what we call the Swedish cube array. And then we also have an IMS station in Stockholm, Ch3, which is yellow scatter points. And this is the observations of radio of xenon 133 during this time period for the 4 different cube stations. And please note that the y-axis differs between the different plots, but most interesting maybe is cube 3, which had a very large peak of 100 millibecquerel, and also cube 4, which had 2 large peaks of 50 millibecquerel, which is very unusual, some of the highest levels we've ever measured. So this was a very large radio xenon release. And this is the situation at the same time period for the IMS stations. So what we have here are measurements from 9 IMS radio xenon stations, which detected CTBTO categorized sea level during this time. And we believe from this work that this radio xenon detected in SCX63, so Stockholm, and also the Norwegian station, NOX49. So the gray and the pink lines here are definitely from this event, but we also suspect that this event was seen in Germany, in Canada, in Japan, and in Mongolia. So what we did when we started to investigate this event was we did some initial investigation where we looked at backwards atmospheric transport models from all of these samples. So this is a snapshot of one of these samples. This is a snapshot of an ATM model, 48 hours from the time the sample was collected. The sample in question is the one indicated by the green arrow. So this means that 48 hours before we collected this sample of radio xenon, this colored area is where the air was. So we did this for all of these samples where we found radio xenon, and this is just an example of 6 such samples. And maybe you can see a trend here. It seemed like all of these samples contained air that arrived from a very similar part, so from east of Sweden. So from this initial investigation, we draw some initial conclusions about kind of like what we would think the source were from. So all the SRS fields indicated that the air from all of these samples during all of this 3-week period came from approximately the same direction. It was east of Sweden. This must have been a really large release, otherwise we wouldn't have seen such high levels, so 100 millibecquerels, it's very, very large. This must have been possibly been an extended release, so something that was continuously releasing radioxenon for days or even weeks. And a final conclusion was that it's very probable or possible or even probable that this was just one source because of how the backwards ATM looked like. To further investigate this, we then did a forward ATM investigation where we had, basically we constructed a grid setup where we had several grid points spread over Middle and Eastern Europe where we suspected the source was from. And for each of these grid points, we ran one forward model per day with 24 hours release. We then varied the level of the source term for each of these day models to best fit the observation, and then added them to compare with the observations. And basically, for this scheme, we fitted each of these grid points with the observations for all of the 4 cubes. So there's a lot of observations from different places that would fit it with each grid point. And this is we used a cost term, if anybody's interested about that looked like this, with the Tikhonov regularization. And once we found our best guess for each of these grid points, we can then compare how well can that grid point predict the measurements. And from this, we can give a score to each of the grid points and find the area that is most likely to contain the source site. So this is what such a result looks like. What is shown on this is a map. The colors represent the Spearman correlation between the grid points and the cube array observations. And then the red area is where we get the best correlation between the models and the observations. Green, a little bit like medium correlation. Blue, lower correlation. And then where there's no colors, basically no correlation. And just to show kind of like what the result of one of these investigations looks like, this is a fit to a site that we know, so a nuclear power plant, in this red area. So this is the Kursk nuclear power plant. And what you see to your left is the observations in the solid lines, solid colored lines. And then the striped black lines is the model fit using Kursk as a source site. And just initial conclusions about this is that, for example, if you use Kursk as a source site, you can fit the observations very well. We basically fit all of the features except this first peak of cube 4 very, very well. So this is a good candidate for potential source. To your right is the source term that would be needed to produce the observations using Kursk. And these are in becquerels per day over the relevant time period. And they are fairly large, between 10 to the power 13 and 10 to the power 14 becquerel of xenon-133 per day that would need to be released. All right, so on to the maybe second interesting thing that we did with this is that we have the cube array, and then we also had the IMS station. So what we could do is we could do exactly the same procedure, but instead of fitting it to all of the cube array, so the 4 stations in the cube array, we only fitted to the SCX-63, so the IMS station observations. So to your left is what you saw before, so the cube array. To your right is the IMS station. And there are basically two very interesting things that happens when you use more stations. Even though the SCX63 station is a more sensitive station, with 6 hours collection time to compare to the 12-hour collection time, using the array, you do shrink this area of very high correlation by about, I think about 75%. So that's the first thing. So you get a smaller area of very high correlation. And the second thing is, you see this high correlation around Stockholm, which is also where the station is located. When you use a grid approach like this, and you only fit to one station, you will always find a perfect solution for a local source. But when you use the grid, you remove this, this probability of a local source. Yeah, so just to conclude, we saw a very large xenon release in November, December 2022. This was seen in both the IMS in the Swedish cube array. And this was, for us, interesting in two ways. Firstly, to understand kind of like what type of levels of xenon do we see in just the background. And this was very much for a CTBTO context. But this was could also be used to showcase the strength of using an array of measurement, so a denser array than the IMS of xenon measurement stations compared to a single IMS station when trying to localize an event. And also we needed a quite high source term to fit these observations, about 10 to 13 becquerel or a little bit more per day. Thank you.
Thank you very much, Sophie, for your presentation. Are there any questions for Sophie? Yes, Suzanne?
Hi, Sophie. That was a really interesting presentation. I noted at the beginning you mentioned that you thought the signal had also been seen on several other IMS stations.
Yes.
And I wondered if you had plans to extend your forward modelling and cost function and to estimate the source to those IMS stations, and whether you felt that the added background that those stations might see might complicate that inversion, or whether it would add to what you've already seen.
Okay, so for your first question, I'm going to advertise a paper which is being written about this, where I've done this. So this has been done. It hits the station. It looks consistent, I would say. For the second part is, these stations are so far away. So we are talking about traveling maybe a week or 2 weeks almost, or like 10 days. And by that time, if you do any backwards modeling, your area is huge. So it doesn't really constrict the area very much. The Norwegian station, NOx 49, for sure could be used in an inversion. But the other ones don't really add a lot of information, because by that time, the xenon has spread so far.
Thank you.
Yep.
Thank you. Yes.
Oh, well, thank you for this very interesting presentation. I might have missed it, but you mentioned in one of the last slides that you used the IMS station solely without adding it to the Kuber measurement stations. Does it improve when you add them together?
No, not very much actually. This has also been done. The area is very similar when you use 5 stations compared to the only 4 cube stations. So we interpreted this as it's being very important that you sample. So basically what you do is when you have a lot of these cubes, is that you sample simultaneously larger part of the plume, and we interpret it as this is the important feature that you add.
Okay, thank you very much, Sophie. We need to move on to our next speaker. Unfortunately, Unfortunately, Matt Goodwin couldn't be with us here today, but he did send us a pre-recorded version of his talk. So we are going to play his talk now and hope that everything works.
Hello there and welcome to this presentation. My name is Matt Goodwin and I'm delivering this presentation on behalf of my collaborators who work for AWE in the UK, FOI in Sweden, PNL in the US, Met Office in the UK and EDF Energy in the UK. This presentation is about the analysis of 12 months of radio xenon monitoring array data in the UK. So the data was collected on a network of Sauna Cube systems which we had deployed around the Hartlepool nuclear power reactor. I'm going to be talking about some of the detections that we've picked up on this network and how we've been analysing the data and attributing the detections to possible sources. A group of collaborators as part of the Xena project came together to study the Hartlepool nuclear power reactor and understand the radionuclide fingerprint of this type of facility. So there are over 300 different nuclear reactors in the world, and in terms of the radionuclide source release parameters, we actually know very little. And this is incredibly important to radionuclide monitoring, to our community, and to the mission of the CTBT. So in this work, we aim to characterize the radionuclide fingerprint of one particular reactor type, which is the Advanced Gas-Cooled Reactor, or AGR. There aren't many of these reactors in the world. They're mostly based in the UK, and one of them is Hartlepool Nuclear Power Station, which has 2 reactors. You can see the photo of when the team was stood on top of one of the pile caps at the Hartlepool station. You can find more information on the background of the project and the overall aims and the work that we've been doing over the last few years in the linked publication here as well. One of the main parts of the project was to deploy a Sauna Cube array around the Hartlepool power station. So you can see from the figure how we configured the systems in the region. Cube 1 was at Bulby, about 24 kilometers east of the reactors, and that was the closest system. Cube 2 was in Durham, which was 30 kilometers to the northwest, and Cube 3 was at Leeds University, which was around about 100 kilometers south. The idea being that this one was a little bit further away. We knew that the background from mainland Europe would be a significant challenge to us, and we hoped that having one system further south and further away from the facilities would possibly catch plumes as they were coming up north from mainland Europe. So here are some of the data from the array. The figure shows Xenon 133 activity concentrations with time. And as you zoom in, you can see that for each of the individual elements of the array or stations on the array, you can see where plumes are passing over not just a single sensor, but the array as a whole. So we consider these to be array detections. And this is really interesting. It's logical to assume that where we've got plumes of detections arriving across the whole array, that the source is not local. Given that Hartlepool Power Station was effectively in the center of the array, this was one of the useful distinguishing features of array type data that we're able to use to determine the possible source and certainly exclude some sources. Now, when Hartlepool Power Station undergoes an outage, possibly to refuel one of the reactors, and across the 2 reactors this happens around about 5 times per year. When this happens, they have to depressurize the reactor core, and this results in a release to the environment through a gas processing route. So these are known as blowdowns, these depressurizations of the reactor. And I've labeled one of the blowdowns that occurred in June, and you can see it occurred just before we had a series of detections across the array. And this was one of the periods that we analysed very, very closely from this data set. Interestingly, this one was not related to the blowdown. So thinking about the analysis toolkit that we have at our disposal, when analysing data like this, we can look at the radionuclide data itself. We need to look for anomalies within that data set. We can compare isotopic activity ratios as well. We can then use stacks data. So there was a stack monitor installed at Hartlepool giving us what we considered ground truth. Can we use that to remove known background interferences. Similarly, we had access to stack data from IRE, which was the biggest source, the biggest nuisance source in the background for us. Of course, we have to use atmospheric transport modeling, or ATM, so we use this in both forward and backward modes. So forward, predict the movement of material in the atmosphere from a known or possible emitter and look at how it contributes to our sensors. And also to backwards or inverse model from a given sample from a given detection and work out a possible source region. We can then try to associate different detections and non-detections that may be related to a given release. And we can put all of this information into source reconstruction software. So in particular, a number of the collaborators were using FRIA to determine source release parameters, i.e. the source magnitude, the location, and the release start and stop time. And we were doing this on background sources, as well as on sources that we thought might be related to Hartlepool. So I mentioned IRE being a significant background source. It's well known and well published that this is a big background source in mainland Europe. So IRE provide STAX data through the STAX project, and this data was invaluable, in fact, in determining the impact of IRE on our sensors. So the figure shows for each of the systems on the array, cube 1, 2, and 3, for the whole, most of the year, you can see the measured xenon 133 activity concentration in black versus the predicted or simulated activity concentration of xenon 133 from IRE. And you can see that a lot of the features that are represented in the time series are mirrored between the measured and the simulated. So here, overall, whilst there are some differences, particularly in magnitude of some of the detections, which usually are related to complex atmospheric conditions, overall, there is a very good agreement, particularly in time. So when a plume arrives as predicted from IRE, and we get detections at the same time, it's very clear to the eye and very useful to be able to see that, well, those detections, whilst the magnitude may be slightly off, are most likely related to the releases from IRE. It's also perhaps even more beneficial to see where there are measured detections with no simulated contribution from IRE, and these prompted further analysis. We also had stack data available from Hartlepool itself, available in two forms. We had measurements of the gaseous activity in core during the powered period and also during the blowdowns. So we could see the activity of the coolant gas in the reactor being reduced as the blowdown occurred. We're also measuring the activity concentrations of gases at the stack through a stack monitor. Both of these are based on high purity germanium detector systems. And the inputs from these measurements were used with atmospheric transport modeling. So the Met Office were able to run atmospheric transport models at very, very high fidelity. So the Met data input that went into these is down at around about 1.5 kilometers on a very, very dense sampling grid. And we were able to track the movement of these releases and compare those with the measured detections on the cube to see if we could positively tie detections on the cube network to releases from Hartlepool. So we're showing some of the plume movement for the March 2022 blowdown, which was the first one that we were measuring for, and also in June 2022, when we thought we saw some detections, but actually turned out they were from IRE. March 22 represents a very interesting period on the cube array. So in the figure, you can see the xenon 133 activity concentrations at cube 1. You can see where we've attributed to various different source sites, and these are based on some input information. So we have some information from reactors such as Heysham in the UK on when they were emitting, and we have some information from STACS on when IRE was emitting, and then filling in the gaps, we were able to determine possible source attributions based on other more generic ATM tools. But in this period, in this what seems like one broad plume of detections, we were able to attribute a number of different sources. And one of those was Hartlepool. There was a detection of around about 7 millibecquerel per meter cubed of xenon-133, and it was only seen on one system. And this system, the measurement agrees incredibly well with the ATM and STACS-led prediction. So you can see the purple is showing the simulated activity concentration, which matches incredibly well with our one measurement. This was our one and only positively attributed detection to Hartlepool throughout the whole year that we were sampling in the UK. There were also a number of other detections across the cube array that were clearly not related to a local source and also weren't explained by the IRE forward simulations. So each of these were investigated in more detail to determine if there was another source in the background. One of those was in December 2022, where there were a series of significant detections across the array. These also coincided with significant detections across the Swedish cube array and on the IMS. Here we used the measurement data and also atmospheric transport simulations from those collections to determine release parameters, possible release parameters using a Bayesian tool known as FRIR. And you can see that the release magnitude must have been fairly significant, around e to the 13 becquerels of xenon-133. And it's fairly well contained the release start time and the release stop time and come up with a likely source. We believe this was a release from a power reactor in this region. This, of course, leads us to consider whether there are benefits in terms of source location and attribution of using an array versus a single sensor or single station like we have on the IMS. So using multiple detects and or non-detects can help constrain a source location and the release parameters. Using the set of detections from December 2022, which I've just shown you, the probability density functions show how the uncertainty in source parameters is reduced when using array type information, and this is compared to a single sensor. So the frequency distributions that you see on the figure here show for in blue where we used a single sensor versus multiple sensors in the array, giving you the results in red. So where does this leave us in terms of the xenon-133 in particular that was measured throughout the radioxenon life cycle? Well, we've got measurements of the core coolant using the GAM system, and there's some published work available on this. From this data set, it's possible to calculate a release magnitude, and this is around 1.4 times 10 to the 10 becquerels in total. We get very similar numbers using the STACS data, which is measuring the gas as it is released. And now we also have in-the-field measurements from this type of facility. So we have detections that, following lots of analysis of many detections, and most of them from the background, we're able to determine one that was solely attributed to Hartlepool reactor, and from this calculate a release magnitude which agrees with the numbers that we had from the core itself. Analyzing this data set was not easy. There were over 350 detections of xenon-133 on the Sauna Cube array for the year that we were measuring. So just one of those detections was definitively linked to Hartlepool Nuclear Power Station. Over 280 other detections have been attributed to at least one facility. In some cases, we were not able to say exactly which facility it was, rather a group of known operating facilities in a given region. Of those, 195 detections were linked to IRE in Fleurus in Belgium. So this is well known that this is a big source in mainland Europe, and it was expected to dominate the background. And the STAX data that was available from IRE was extremely useful in identifying which detections were from IRE emissions. So a measurement campaign such as this has focused on Hartlepool Nuclear Power Station, but it would not have been successful without this STAX data from IRE due to the sheer number of detections that we were able to attribute to the background. For Xenon-133 detections identified on the array and ATM simulations, it was possible to confirm the total release magnitude, which then agreed well with calculated releases from the source. In the period that we were sampling, the Hartlepool reactors had very few operational difficulties, and as such, there were no unplanned releases of radioxenon. So this confirms a very binary nature of HER emissions, and where we may be tempted to use a daily average for all types of nuclear facility, some facilities, and AGR being one of them, this is not a good model for. That concludes my presentation. Thank you for listening. Look out for our latest paper, which is currently being revised for publication in the Journal of Environmental Radioactivity. And this is a look at all of these measurements, and we hope to publish all of the source attributions that we've been able to determine. If you'd like to get involved in work like this, we're also setting up a new project which is looking at characterizing the radionuclide fingerprint of a pressurized water-cooled reactor, or PWR. This, of course, being the most abundant reactor type in the world, is a lot more applicable to the world as a whole. There's a post available on this, P5.1371. Please reach out to my colleagues from AWE who will be available in person to talk to you about this. Thank you.
Okay, we have to do the questions a little bit differently here because Matt obviously isn't with us, but we have Dan Chester here, who is also involved in this project, who may or may not be able to answer your questions depending on what they might be, who's graciously offered to field some questions. So does anyone have any questions for Dan?
Is he here?
I think he's here. Well, he said he was going to be here, but he may not be here. It's not you? I don't see him. Okay. All right. This was our final speaker of the session. I'd like to thank everyone who came and gave a talk today. Thank you very much. Your contributions have been very appreciated. This was a very interesting session, and I'd like to give one more round of applause to all the speakers today. So with that, we will close the session, and I hope to see you all around in the days to come.
And the poster session.
Yeah,
No, it's okay.